My name is Zhengyang Fei, and today I will be presenting my review on the paper, A Brief Introduction on Latent Variable-Based Ordinal Regression Models with an Application to Survey Data by Wieditz et al. This presentation is structured as follows. We will start with an introduction to the topic, followed by an overview of ordinal regression. Then, we will discuss the methodologies used, examine its application in a pediatric consent survey, explore advanced discussions including model selection and generalizations, and finally conclude with the key takeaways. Ordinal regression is a crucial technique for analyzing ordered categorical data, such as Likert scale responses, where the categories have a natural ranking but no fixed numerical distance between them. Traditional linear regression is unsuitable for such data because it violates key assumptions, including the assumption of constant variability and the potential for generating predicted values that fall outside the defined ordinal categories. We can imagine a scenario where we are predicting customer satisfaction on a scale of 1 to 5. If variability is constant, the spread of ratings should be the same across all predictor levels. However, in reality, lower-income customers may exhibit a wider range of responses due to varying experiences, while high-income customers may constantly provide higher ratings, leading to heteroscedasticity. This violates the assumption of constant variability, making linear regression unsuitable. One possible approach to address these limitations is to use latent variable-based ordinal regression, as explored in this paper. In ordinal regression, the response variable, y, is categorical and has an inherent order. Oftentimes, it has more than 2 levels. To model appropriately, we introduce an underlying continuous latent variable S, which is the unobserved construct influence the ordinal response. The observed categories of Y are then determined by predefined threshold cut points theta that partition the continuous space of S into discrete ordinal levels. Mathematically, Y is assigned a category based on an underlying continuous latent variable S. The observed ordinal levels of Y are determined by threshold cut points theta, which follow a strictly increasing order. For a categorical variable with L levels, L-1 cut points are required. The probability distribution for an ordinal response with 5 categories is illustrated in the graph. We define our model as S equals to x beta plus epsilon, where x is a vector of covariates, beta represents the regression parameters, and epsilon is a random error term. This formulation enables us to estimate the influence of covariates on the latent variable. Several link functions can be used in ordinal regression. If we assume a standard normal distribution for the epsilon, we will obtain the ordinal probit model. If we assume a logistic function, we will obtain the ordered logistic regression model using a similar mathematical derivation. And more generally, a cumulative link model is used for various error distributions. For instance, the complementary log-log link used when higher categories are more probable. The negative complementary log-log link reverses the complementary log-log link for when lower categories are more probable. The quotient link, which has heavier tails compared to the normal distribution, making it more robust to outliers. Unlike linear regression, ordinal regression does not include an intercept term, as it would shift both the latent distribution S and the threshold cut points, making it unidentifiable. Hence, it is assumed the intercept is at 0. Let the vector x be the vector of covariates and x tilde be the same vector, only differing by 1 on the kth covariates. This derivation allows us to determine the effects of a unit change in the predictor variable. The exponential function of beta k represents the cumulative odds ratio, showing the multiplicative effects of an increase in the predictor variable. We did applied ordinal regression to a survey investigating parent willingness to consent to pediatric anesthesia studies. The survey presented parents with 3 types of research designs, each increasing in complexity. The first was an observational study, the second a randomized controlled trial, and third a pharmacological study. Parents' responses were captured using a 5-point Likert scale, ranging from absolutely consent to absolutely decline, allowing for a structured assessment of their willingness to participate. Here is a glimpse of the data, as well as the covariates of interest. Our baseline model includes study complexity and child sex as covariates, with the observational study serving as the reference group. Results indicated that study complexity had a significant difference compared to the baseline observed study group. We can also interpret the study coefficient estimate. For example, RCT shifts the latent response distribution, in particular, the mean, which is represented by the dashed line, is shifted to the right by 2.2127 units. The estimated response probabilities are displayed then in a stratified manner, where the horizontal axis represents the study complexity levels, observational, randomized controlled trial, and pharmacological study, while the vertical axis represents the child's sex. This stratification allows us to observe how the probability distribution shifts across different study types and gender groups. In the observational study, we can see that a significant proportion of parents indicated absolutely consent as their responses. However, for the randomized controlled trial, the number of parents choosing absolutely consent was lower, and it was the lowest for the pharmacological study. This downward trend in willingness to consent is consistently observed across both male and female groups, suggesting that the study complexity plays a critical role in parental decision-making. To compare the study groups RCT and Pharma, which was not directly observable in the summary of the baseline model, we applied a separate function. Simultaneously, we utilized Tukey's method to adjust for multiple comparisons. This approach allowed us to examine pairwise differences, revealing that all comparisons were statistically significant, further reinforcing the impact of study complexity on parental consent. Interaction effects between study complexity and sex was tested using an ANOVA-based likelihood ratio test, finding no strong evidence of interaction. Similarly, subject-specific random effects was examined, with results indicating no substantial variation in individual response behavior. WEDITS extended the model by incorporating continuous covariates, specifically parental age, as an additional predictor. When multiple parental figures were present, the model considered the age of the oldest parent to represent the household's decision-making authority. The graphical representation illustrates how a continuous predictor influences the latent variable distribution. Specifically, as the predictor variable, parental age, changes from x prime to x prime prime, the latent variable distribution S shifts by x prime prime minus x prime times beta units, highlighting the effects of the continuous predictor on the outcome. For goodness of fit, WEDITS recommended 3 tests by Fagerland, Hosmer, and Horrell, including the Lipschitz test and Pochsteiner-Robinson test. Note that these tests do not have a good power to detect a particular type of lack of fit. Particularly, a large value of the global fit statistic only indicates some lack of fit, but does not provide insight about its nature. For an elaborate discussion about these tests, the author refers to Fagerland and Hosmer in the bibliography section. Horrell suggests using graphical techniques such as nomograms to check for the proportional odds assumption, which is the main assumption of the ordered per bit model. Sample size calculations, WEDITS recommended using the H-MISC package and discussed model generalizations such as alternative link functions and nonlinear ordinal regression models. To summarize, we began by introducing the need for ordinal regression when dealing with ordered categorical data and discussed why traditional linear regression is not appropriate. We then explored the mathematical foundations of latent variable-based ordinal regression, highlighting its reliance on an underlying continuous construct divided by threshold cut points. Various link functions were introduced, including ordered per bit, ordered logit, and alternative link functions such as the complementary log-log and quotient, each suited for different distributions of ordinal responses. We then applied these methods to a real-world survey on pediatric consent, demonstrating how study complexity and parental factors influence decision-making. Advanced discussions covered model selections, goodness of fit tests, and generalizations to nonlinear ordinal regression models. Overall, latent variable-based regression provides a powerful framework for analyzing ordinal outcomes, making it a valuable tool in various research domains. Thank you for your attention. For more details, please refer to the original paper by WEDITS et al.